Okay, what is the pH of the solution which results from mixing 75 milliliters of 0.5 molar ammonia and 75 milliliters of 0.5 molar hydrochloric acid? So what we have here is the reaction between ammonia, a weak base, and hydrochloric acid, which is a strong acid, to produce ammonium ion in solution with water, of course. So when the ammonia reacts with the hydrochloric acid, since we have equal amounts, then all of the ammonia is going to react, and we're just going to be left with this aqueous ammonium ion solution. So I've written the equation for that right here. We have ammonium ion, okay, and in water, and it's going to dissociate somewhat into ammonia and hydronium ion. And here's the Kb for that reaction. So first let's determine the amount of ammonia and hydrochloric acid that result. Again, remember in this case we have equal amounts of acid and base, so we're going to end up with an acidic solution due to the ammonium ion. So the moles of ammonia will be equal to the volume of ammonia, which is 75 milliliters, and then we can multiply that by the molarity. Remember, we have to convert the 75 milliliters to liters. Here we have 0.5 moles per liter of ammonia, and that gives us 0.0375 moles of ammonia. We can calculate the moles of hydrochloric acid the same way, because again we have equal amounts. And let's see here, made a mistake there. And that's going to give us 0.0375 moles of hydrochloric acid. So what we are interested in is the amount of ammonium ion that's produced, okay, after this reaction is completed. So let's see here. The moles of ammonium ion, it's going to be equal to the moles of ammonia that was reacted. So moles of ammonium ion, that will be 0.0375 moles. Now what we need is the concentration of ammonium ion, and then we're all set to go. The concentration is going to be the number of moles of ammonium ion produced divided by the total volume. So the total volume is the 75 milliliters of ammonia plus the 75 milliliters of the hydrochloric acid. So that would produce 150 milliliters of solution. So we'll go ahead and convert that to liters. And we end up with a molarity of 0.25 molar. So now I'm ready to set up my ICE table. Again, the important thing was determining the concentration of ammonium ion. So here we have this, and let's see. Oops, it's not correct. Let me erase that. So here we have ammonia and hydronium ion, because some of this ammonium ion is going to dissociate, okay? A very small amount, because remember Kb here is going to be is small. Now, one other piece of information we need here is we need the acid dissociation constant for this. We're given Kb, and remember the relationship between Ka and Kb is Kw, which is 1 times 10 to the negative 14, So let's go ahead and solve for that. So we have 1 times 10 to the negative 14 divided by KB, 1.8 times 10 to the negative 5th. And that's going to give me 5.56 times 10 to the negative 10. So as we can see, Ka is very small. And so we're not going to have much dissociation here. So let me rewrite the equation again so I can set up the ICE table. So we have our initial change in equilibrium. So initially we have 0.25 molar ammonium ion. And it's going to decrease by some amount x. And then here we're going to have an increase by some amount x. And then at equilibrium. And this will just be x and then x. So let's go ahead and set up our expression here. So Ka is 5.56 times 10 to the negative 10. And that's going to be equal to x squared over 0.25 minus x. Okay. Now, I can definitely simplify this. I'm going to assume that x is very, very small. And so it's not going to affect the initial concentration. So this is just going to be approximately equal to 0.25. And x will definitely be negligible in this case because look at our dissociation constant. It's 10 to the negative 10. So this allows me to simplify our expression. 5.56 times 10 to the negative 10 is equal to x squared over 0.25. And we'll go ahead then and solve this for x. And I get x equal to 1.18 times 10 to the negative 5. And we know that x is equal to the hydronium ion concentration. So from that, I can determine the pH of the solution. And 1.18 times 10 to the negative 5. And that gives us a 4.93. Now, one thing we do need to do here is test our assumption. So we'll go back up here. And let's go ahead and plug in 1.18 times 10 to the negative 5 for x. And that equals 0.25. So our assumption was valid. If the assumption would not have been valid, then we would have needed to use the quadratic formula.